In 1961, 6 foreign-built locomotives arrived on American soil, carrying more than freight capacity. They carried a bold gamble, a clash of engineering cultures, and a promise that the brutal math of mountain railroading could finally be rewritten. Within a few years, that promise would dissolve inside overheated tunnels high in the Rockies, leaving behind one surviving engine and a lesson that still echoes today. By the late 1950s, railroads fighting their way across the Rocky Mountains were trapped in a punishing routine that felt impossible to escape. Moving a mile-long freight train up a steady 2% grade demanded brute force, and brute force meant numbers that bordered on absurd. Crews often coupled together 8, sometimes even 10, diesel-electric locomotives to drag tonnage uphill. Each locomotive carried 16 pistons, so a full lash-up meant 160 pistons pounding away for hours, 40 traction motors spinning beneath the frames, and 10 separate electrical systems stitched together in a fragile chain where any single failure could stall the entire train. Maintenance shops lived in a constant state of triage. In places like Roseville, mechanics spent long nights crawling through cramped engine compartments, replacing cracked piston rings, swapping burned fuses, resurfacing worn commutators, and chasing electrical faults that seemed to multiply with every trip through the mountains. Logbooks read like battlefield reports, listing traction motors shorting out, turbochargers overheating, crankcases leaking, and generators flashing over under heavy load. When one locomotive in a 10-unit consist failed, the entire train could be stranded on a grade, blocking traffic and tying up crews while dispatchers scrambled to send relief power. Every hour lost meant angry shippers, missed connections, and rising costs that stacked up faster than freight cars in a yard. Executives watched the numbers and saw a simple but ruthless equation. Multiply the weak links by 10, and the odds of a flawless run collapsed. Add in growing freight volumes and mounting pressure from stockholders demanding efficiency, and the old solution of adding another locomotive started to look like a strategy with no future. American builders such as General Motors' Electromotive division and General Electric kept promising more powerful engines, yet nothing reliably broke through the 2,000 horsepower ceiling without raising fears of catastrophic breakdowns. The mountains were not getting any lower, and the trains were not getting any lighter. Inside corporate offices at Southern Pacific and Denver and Rio Grande Western, discussions turned serious. Charts covered conference tables, projecting fuel consumption, crew costs, and maintenance expenses. Under different scenarios, the dream was straightforward. Replace a string of underpowered locomotives with a single machine capable of doing the same work. Fewer engines would mean fewer crews, fewer moving parts, and fewer opportunities for something to go wrong. The problem was that no American manufacturer could offer a 4,000 horsepower locomotive ready for mountain duty. That search for muscle led across the Atlantic. European trade journals began appearing on executives' desks, filled with reports of German precision engineering and post-war industrial revival. One name surfaced repeatedly: Krauss-Maffei, a company based in Munich that had rebuilt its reputation in peacetime after producing armored vehicles during the war. Their flagship diesel hydraulic locomotive, the ML4000, promised more than double the horsepower of most American road engines, and did so with a radically different approach to transmitting power. Instead of using a diesel engine to spin a generator that fed electricity to traction motors, the German design relied on hydraulics. Beneath the streamlined shell sat 2 Maybach MD870V16 diesel engines, each a 16-cylinder 4-stroke unit built for sustained high output. Together, they generated 3,540 horsepower, a staggering figure for the era. Rather than sending that power through a generator, each engine drove into a Voith L63 zero hydrodynamic torque converter, a massive device filled with specially formulated oil engineered to withstand extreme pressure. The concept sounded elegant. The engine spun a pump that hurled oil at a turbine, and the force of the fluid turned the output shaft without direct metal-to-metal contact. There were no traction motors under the axles, no high-voltage cables snaking through the frame, and no risk of electrical flashovers under heavy load. Thick steel cardan shafts carried power from the transmission to the wheel sets, resembling components found beneath heavy-duty trucks rather than traditional American locomotives. On paper, the ML4000 could deliver tremendous torque at low speeds, ideal for starting heavy trains on steep grades without frying motors or blowing fuses. Hydraulic drive also brought a philosophical shift. In the German view, fluid could absorb shock and smooth out fluctuations in load. If wheels slipped on wet rail, the oil in the converter would respond naturally, spinning faster and dissipating energy instead of burning out hardware. In Europe, where tunnels were shorter and ventilation more forgiving, this system had built a reputation for reliability and efficiency. For American executives weary of endless electrical failures, the appeal was obvious. The decision to import 6 of these experimental locomotives carried symbolic weight as well as financial risk. When the units arrived at the port of Houston on October 31st, 1961, the scene drew crowds of reporters and railroad employees. The sleek, rounded bodies and turret-like cabs looked unlike anything produced in Detroit. The Krauss-Maffei name on the sides sparked curiosity and unease, a reminder of wartime industry now repurposed for commercial railroading. Yet the spectacle also carried hope. If these machines could tame the Rockies, the old arithmetic of 10 engines per train might finally be erased. Early tests on the flatlands of Texas seemed to validate the gamble. On level track, the ML4000 locomotives demonstrated impressive pulling power. Engineers reported smooth acceleration and a quieter cab environment without the familiar whine of traction motors or flicker of overloaded circuits. 3 of the German engines could replace 8 older F7 units while hauling comparable tonnage, reducing the number of moving parts and simplifying crew assignments. Maintenance calls dropped during these initial runs, and the hydraulic transmissions absorbed the shock of heavy starts without scorching wiring or burning out motors. Encouraged by these results, management assigned the locomotives to increasingly demanding service. Field reports described German engineers riding along, carefully noting temperature readings, vibration patterns, and fluid pressures. Confidence grew as trains rolled out of Houston and San Antonio under the distinctive rumble of twin Maybach engines. The real test, however, waited hundreds of miles to the northwest, inside the long tunnels that cut through the spine of the Rockies. The confrontation came in places like the Moffat Tunnel, stretching more than 6 miles through solid mountain. A steady 2% grade forced trains to crawl at low speeds, sometimes around 10 miles per hour, turning the locomotive into a piston, pushing against a column of trapped air. Exhaust temperatures could reach 800 degrees Fahrenheit, and the confined space offered little chance for heat to escape. American diesel electrics had endured these conditions for years, but the hydraulic ML4000 faced a different set of challenges. As one of the German locomotives entered the tunnel under heavy load, exhaust gases accumulated and began to roll back along the roofline. The air intakes, positioned near the top of the locomotive behind the engines, drew in increasingly hot, oxygen-poor air mixed with its own fumes. Combustion suffered and power output dropped. Inside the cab, crews reported the sting of diesel smoke and the glow of warning lights as oil temperatures climbed. The Voith torque converter, dependent on stable fluid properties, faced mounting stress. The specialized hydraulic oil that performed flawlessly in European service began to thin and aerate under extreme heat. With limited airflow to cool the system, temperatures pushed past safe limits. In some instances, the oil vaporized, disrupting the closed-loop flow that made the design possible. Instead of liquid muscle transferring torque, the transmission filled with bubbles and pressure spikes. Compounding the crisis, the locomotives relied on pneumatic control systems routed through sections of the engine compartment exposed to intense heat. Rubber and plastic airlines softened and, in some cases, failed. When air pressure dropped, valves controlling throttle settings and brakes malfunctioned. Crews described situations where brakes refused to release or throttle responses became erratic. In the most severe cases, the locomotive shut down entirely inside the tunnel, leaving crews stranded in darkness with metal ticking as it cooled and smoke hanging in the stale air. Rescue operations often required conventional American diesel electrics to tow the disabled ML4000 units out of the tunnel. Each incident eroded confidence. The mechanics now faced a different kind of challenge, as replacement parts for Maybach engines and Voith transmissions had to be shipped from Germany, delayed by ocean transit and customs procedures. A single failed pneumatic valve could sideline a locomotive for weeks, disrupting schedules and undermining the cost savings once projected in boardrooms. American maintenance practices also clashed with the precision demanded by the German design. The ML4000 required tight tolerances, specialized fluids, and metric fasteners unfamiliar to many shop crews, accustomed to rugged, diesel-electric systems built for rapid field repairs. Misalignments, fluid leaks, and warped panels appeared more frequently as the locomotives accumulated miles under punishing mountain conditions. The very complexity that allowed hydraulic drive to function so smoothly in Europe became a liability in the harsh and unpredictable environment of the American West. As breakdowns mounted, dispatchers quietly reassigned the German locomotives to flatter routes whenever possible, avoiding extended tunnel runs. Meanwhile, domestic manufacturers accelerated their own development programs. Within 2 years, models such as the EMD SD45 and the GEU 25B emerged from American factories, offering higher horsepower while retaining proven diesel-electric architecture capable of surviving extreme heat and thin mountain air. Market sentiment shifted rapidly. Orders for imported hydraulic locomotives evaporated as railroads opted for upgraded domestic designs that fit established maintenance practices and supply chains. By 1968, nearly all of the 6 ML4000 units had been retired and cut up for scrap, their cardan shafts and Maybach components dispersed as curiosities rather than cornerstones of a new era. One locomotive survived the purge. Southern Pacific 9010 avoided the scrapper and eventually found preservation in California, restored by volunteers who recognized both its ambition and its cautionary tale. The machine stands today as a reminder of a bold experiment that sought to rewrite the rules of mountain railroading and instead revealed the unforgiving nature of the terrain it aimed to conquer. American railroads continue to evaluate new technologies through the lens of geography and climate. Whether the innovation involves hydrogen fuel cells, battery electric systems, or advanced automation, the Rockies remain an unblinking test site where laboratory promise must prove itself against heat, grade, and confined air. The story of the 6 imported hydraulic locomotives underscores a principle that transcends eras and equipment. Engineering brilliance carries weight only when it can endure the environment that challenges it.